Okay, so this swag shout out goes to my favorite liberal, Sid. Hey Sid, two subatomic particles walk into a bar. The proton says to the neutron, you know, they got really great hamburgers here. And the neutron says, are you sure? And the proton says, I'm positive. Okay, anyways, so back to physics, chapter 4, section 2. We're going to be talking about Newton's second law, and we're talking about this idea of weight and apparent weight and weightlessness and that type of thing. We're going to talk about a concept called viscosity. Viscosity is a fluid's resistance to flowing. The more viscous something is, we would think of it as being thicker. Molasses is really viscous, so it doesn't flow very much. Oil is somewhat viscous. Now, don't confuse that with weight. Oil will float on top of water because it's less dense. However, it is more viscous. It'll take a longer time to flow. Anyways, we're going to be talking about some of that stuff here. So what is weight? Weight then is gravitational force experienced by the object. Force, the weight is a force. Mass is not a force. Weight, on the other hand, is a force. And we're going to say that the force G is equal to m. M is the mass of the object times G, which is the gravitational field, the acceleration due to the gravitational field. So the gravitational field then is a vector quantity that reflects the mass of an object to the gravitational force it experiences. Near the Earth, we say that G is going to equal 1.8 newtons per kilogram towards the center of the Earth. That's where we get that 1.8. We're going to round it up to 10 most of the time. When you step on a scale, the scale is pushing up on you with an equal magnitude of weight that you're pushing down on it due to gravitational forces. The scale is calibrated then to convert the stretch of the springs and the force necessary to give a net force of 0. In other words, you're not accelerating up, you're not accelerating down. So let's take a look at this little thing on weightlessness.
What do you think is weight? Because the weight force is defined as Fg equals mg, Fg changes when g varies. On or near the surface of Earth, g is approximately constant, so an object's weight does not change appreciably as it moves around near Earth's surface. What happens if you stand on a scale in an elevator? As long as the elevator is in equilibrium, which means the net force acting on it is 0, the scale will read your weight. What would the scale read if the elevator accelerates upward? You are the system, and upward is the positive direction. Because the acceleration of the system is upward, the upward force of the scale must be greater than the downward force of your weight. Therefore, the scale reading is greater than your weight. If you ride in an elevator like this, you would feel heavier because the floor would press harder on your feet. On the other hand, if the acceleration is downward, then you would feel lighter, and the scale would have a lower reading. The force exerted by the scale is called the apparent weight. An object's apparent weight is the force an object experiences as a result of all the forces acting on it, giving the object acceleration. Imagine that the cable holding the elevator breaks. What would the scale read then? The scale and you would both accelerate with A is equal to minus G. According to this formula, the scale would read 0, and your apparent weight would be 0. That is, you would be weightless. However, weightlessness does not mean that an object's weight is actually 0. Rather, it means that there are no contact forces pushing up on the object, and the object's apparent weight is 0.
Okay, so let's talk briefly about drag forces then. When an object is moving through a fluid, now air can be a fluid, okay? It's just basically anything that kind of moves out of the way when you move through it. you're going to experience a drag force. When you're try to move through water, you're experiencing a lot more drag force than you are through air. The drag force is a force that's exerted by the fluid on an object trying to move through it, and it acts in the opposite direction to motion. The force depends on the motion of the object, the properties of the object, whether it's streamlined or not, the properties of the fluid, how viscous it is, and the object that is moving through. So, for instance, if we drop a tennis ball, viscosity increases, and so does the drag force. So, the constant velocity is reached when the drag force equals the force of gravity. We call this terminal velocity. Here's another little video on that.
Drag force and terminal velocity. If you drop a table tennis ball, as shown above, it has very little velocity at the start, and thus only a small drag force. The downward force of gravity is much stronger than the upward drag force, so there is a downward acceleration. As the ball's velocity increases, so does the drag force. Soon, the drag force equals the force of gravity. When this happens, there is no net force, and so there is no acceleration.
Okay, so that's drag force. And this whole idea of drag force, by the way, and terminal velocity, if you're a skydiver and you jump out of a plane and you spread out, arms and legs out, you'll achieve a terminal velocity of about 120 miles an hour, and then you don't fall any faster than that, and then of course you would pull your ripcord. So anyway, so that's drag force. That's it.